All right, so here's another problem, and there's a lot of little, I call them curveballs in this one, so that's why I want to do it. So a block of mass m1 equals 2.6 kilograms rests upon a rough incline, so we have friction, that is angled at 30 degrees above the horizontal. A massless cord is connected from this block over a massless and frictionless pulley. Now that's awesome, right? Because it means that the magnitude of this tension equals the magnitude of that tension. All right, to another block of mass m2 equals 2.2 kilograms. That is hanging freely 2 meters above the ground. The coefficient of kinetic friction is 0.18. If the blocks are initially at rest, how long does it take for block 2 to reach the ground? So it's a kinematics problem, right? Just a good old kinematics problem. Well, you know it's not that simple. Okay, so what's the object? Which one do we care about, block 1 or block 2? Well, we care about this one, right? Because we want to know how long it's going to take for this one to reach the ground. So we're just going to draw a pictorial representation for M2. Now, for reasons which I'll explain shortly, this is going this way, correct? And it's, we can choose any coordinate system we want. Well, I think it's much easier if we just make it so the acceleration is always positive. So we're going to make down plus, up minus. So the acceleration of this thing will be positive. And again, I'll explain a little bit more as we go along. All right, so this is the pictorial representation for M2. So the coordinate system plus minus. So it's not the one that Randy Knight uses. Okay, forget about the motion diagram. So how many points do we need? It's at rest here, and then we want to see how long it takes to reach this point. So we just need 2 points. So 2 points. So y0, v0, t0, y1, v1, t1. Okay, where do you want to put the origin? Doesn't matter. I'm going to put it here, and it's nothing special. I just feel like it. So there's the origin. And again, it's accelerating this way. So I might as well draw my little a. All right, so again, everything I do here is just to help me not make a mistake later on. Okay, so this is my origin, and it's at rest. So I know y0 equals v0 equals t0 equals 0. Well, that's nice. Okay, now what's y1? 2 meters. And why is it positive 2 meters? Why not negative? Because of my choice of coordinate system. So again, I just want to emphasize it's crucial that you draw that just so you remind yourself what's going on. We don't know what V1 is, and we don't know what T1 is. But what do we want to know? We want to know T1. Okay, so we know both y's. We want to know a t. We don't know the final velocity. What would be a good equation to use? The long one, right? The second one. So we're going to use y final equals y initial plus v initial delta t plus 1/2 a delta t squared. Well, all right, so let's just plug everything in. So y final is y1. Okay, y initial is 0, v initial is 0. Delta t is just t1 minus t0, which is just t1. So basically that goes away, and we just have y1 equals 1/2 a t1 squared. So therefore t1 equals 2y1 over a square root. All right, we're done. Don't you wish? Okay, so that's what we're looking for, right? And we're not surprised. We have to find a. I mean, that's the whole point of this chapter, right? Using Newton's second law, force diagrams to find A. So we have to find A. All right, not a big deal. So, we keep working with M2. All right, so now we're going to do the force diagram. So, what are the forces acting on M2? There's tension and there's gravity. So there's tension. Now, M2G. Okay, so this is a common problem for new physics students. They forget to put the little subscript. You got to put the little subscript, the 2, M2G. If you don't, later on in the algebra, you might be canceling masses and they're not, you can't cancel, they're different, okay? All right, and again, I want my A this way, and I want it to be positive, so I'm still using this coordinate system. All right, I'm still going to use the non-Randy Knight coordinate system. All right. Okay, so there we go. I'm still working on M2. So here we go. So the sum of the y forces using this coordinate system is M2G, which is positive, minus T. Now, is this equilibrium or non-equilibrium? It's non-equilibrium. It's accelerating. So I don't put 0, I put M2A. All right, so there, what do I want? I want A. So let's do it over here. So divide everything by M2. So we have, okay, so I'm going to divide everything by M2. So that's just going to be a G, that's going to be a T over M2. So I'm going to have a G minus T over M2 equals A. All right, so I'm done, right? No, I'm not done. How come I'm not done? Because I don't know what T is, right? I don't know what T is. Rats. Okay, not a problem. So what am I going to do now? I got to make a force diagram for M1. Okay. So let's do that. Okay, so now I'm going to tell my brain I'm working on M1, right? Because I don't want to goof up. All right. And now, I'm going to use a tilted coordinate system. That should be obvious. And I'm just going to use a Randy Knight coordinate system, right? Because it's going to accelerate this way. And I want the acceleration to be positive. Why? Well, why not? I mean, first of all, this acceleration is going to be the same as that, right? Magnitude-wise? Of course it is, right? I mean, the string doesn't, it's not a bungee cord or something like that. So this acceleration magnitude is going to equal that acceleration magnitude. So that's what I mean. It kind of makes sense to have this positive, but if I want this to be positive, which is what I always do, then I want that to be positive because I don't want an A1 and I don't want an A2, I just want an A. All right? Okay, so here we go. So what are the forces acting on M1? Well, there's T, and there's a normal, and there's weight. There's always weight. That's a W, sorry. Weight, we're down here. And now there's friction, rats. And what kind of friction is it? It's moving, so it's kinetic friction. And you notice, I'm not careful at all about the magnitude of my vectors. I think it's a waste of time. I mean, you just do this to guide your mathematics, okay? So I don't, if I were writing a textbook, I'd have the magnitudes all perfect, but waste of time. And I'll get my angle. All right, and let's see. I'm tilted coordinate system, obviously, so I gotta resolve this weight, right? So I have a piece there and a piece there. So this is W cos theta, and that's W sine theta. Okay, wow. Now look, in our x equation, we have friction. Friction always has the normal force in it, right? Fk equals mu k n. So whenever you have a problem with friction, you have to solve for the normal force. I mean, you have to know what the normal force is. And the normal force is generally going to be in the y direction, right? So all I'm saying is it's a good idea to do the y equation first and to get the normal force, and then you can do the x equation. All right, so here we go. So I'm going to, all right, so it's kind of, all right, okay. So here we go. So the y equation. So the sum of the y forces, again, rainy night, so we have n going up. We have w cosine going down. Let me just put mg minus mg cosine theta going down. And that's it. And now look at, is this thing, is m1 accelerating this way? No. So the sum of the forces equals 0, right? It's equilibrium this direction. So I'm going to say this is equal to 0. So therefore, what's my normal? So my normal is mg cos theta. All right? Okay, I'm going to use that in a couple of minutes. Now I do my x. Okay, so the sum of the x forces. Okay, I have my t going that way. I have my w sine theta going that way. So minus mg sine theta. And I have my fk going down, or I mean negative x, minus fk. And what does that equal? Well, you know, I mean, this thing is accelerating, right? So it equals m1a. Equals m1a. And again, I've seen it again and again. People forget to put the subscript. Okay, now, wonderful. We want tension. So solve for tension. So tension, just put all this junk on the other side. So it's m1a plus mg sine theta plus fk. All right, now, what is fk? Because we got to substitute for it, right? So I just wrote it a minute ago. So fk is mu kn. Well, so that's mu k. All right, where's our normal? Right here. So it's mu k mg cos theta. Okay, so we got to substitute that. So we have mu k mg cos theta. All right, let's see if I agree with myself. mg, oh, I see, look at, even see, what did I forget to put? Subscript. Subscript. Don't do that. Subscript. Oh, golly. Okay, m1g sine theta, mu k, m1g cos theta, m1a. Great. All right. So now I'm feeling happy, right? Because now I wanted to get the tension, because that's what I needed, right, to solve for A. So I got to stick this T up there. Oh, my goodness. A lot of algebra. So I have G minus this whole thing, right? So let me write it. We want to get A, right? So let me just write A. So I have A equals G minus this whole mass divided by M2. So I have minus M1A plus M1G sine theta plus mu k M1G cos theta. That whole thing divided by M2. Oh my. All right? Now, I hope you realize what a mess this is, because here I have an A, here I have an A. And we're trying to solve for A, right? So I still have some math to do, right? I'm trying to solve for A. So I got to work with this to get A. And I ran out of board space, so that's kind of how it is. All right, so that's all right. Okay, so I'm going to write this up here. Actually, I can erase all this stuff. Okay, so I got to solve for A, but I have an A here and I have an A here. So I think it's going to be easier if I break this thing up, right, into individual pieces. So I'm going to, all right, so I'm going to do that. So A equals G minus, so M1A divided by M2. M1A over M2. Then I have a minus M1G sine theta over M2. Then I have a minus mu k M1G cos theta over M2. Okay, here's another place where people mess up. So just math, you know, here's a minus sign, right? And so you got to carry that minus sign everywhere. Minus, 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 right? All right? So minus, minus, minus. All right. Let's see if I messed up. I didn't. What do you know? Okay, so what we want to do is solve for A. So we're going to get this guy on the other side. So I'll have A plus M1A over M2 equals all that junk. Right, so I just put this on the left. G minus M1. Okay, let's save a little time here. Good golly. Yeah, let's do some factoring. All right, so we put this on the left. We have a G, then we have minus M1G over M2 sine theta plus mu k cos theta, right? I just factored out the M1G over M2. So I have a minus sine, and then I have a minus times a plus is a minus mu k cos. All right, okay, all right, so that's good. Okay, now remember we want to solve for A, so we got to factor it out. 1 plus M1 over M2 equals all this junk. All right, now to get A, we're going to divide by this. Okay, and there's our equation. Whoa! And I'm done, right? I mean, I could simplify it more, right? I could multiply. Let's just simplify it a little bit more. That's just for fun, you know? Math is fun, right? Let's multiply top and bottom by M2, just so we get rid of these stupid fractions, right? So multiply top and bottom by M2. So it's going to be M2, that goes away. That's going to be M2, that goes away. Yeah, it's nicer, don't you think? I think so. Okay, I'm done. All right, I'm not going to, that's it. Okay, now what are we going to do? We're going to plug in the numbers, right? We're going to plug in the numbers. You're not going to believe what the answer is. So you plug in all these numbers. Hopefully I didn't do it wrong. But you plug in all these numbers, and guess what A equals? 1 meter per second squared. Who'd have ever thought, right? It's funny. That's what it comes out to be if I didn't. Okay. All right, so now we'll go over here. And so T1 equals square root of course, I erased everything. What was Y1? Let's see, Y1 was 2 meters. So we have 2 times 2 meters over 1 meter per second squared. And that comes out to be 2, right? 2. Because 2 times 2 is 4, square root of 4 is 2. So 2 seconds. That's the answer. Yay! All right, so there you go. So I told you that there's going to be a lot of algebra in these problems, right? They're going to be long. And, I mean, the physics isn't all that hard, but there's a lot of algebra. But in my opinion, the easiest way to do this is, again, use different coordinate systems so that A is positive for each object. So this is a tilted Randy Knight coordinate system, and this is a non-Randy Knight coordinate system, right? Right? This is plus, minus. But it's just easier because the A's are the same. And again, you know, you have your free agency. You can do it Randy Knight's way and have 2 different A's. I don't really care, as long as you get the right answer, right? Okay, so there's a lot of math, so get used to it. So I mean, look, I write pretty small. It took an entire page. So these problems are going to be long. That's all I'm saying. They're going to be long, and you should expect that. I don't generally give the long ones on the exams, but I give but sometimes you get a long one on the homework, and it's good because part of the purpose for this class is to help you improve your problem solving, you know, your math skills. It's not just math, it's problem solving, which includes math. Okay, woo, that was a good one. Let's do another good one. All right. A 2-kilogram steel block is at rest on a steel table. A horizontal string pulls on the block. What is the minimum string tension to move the block? Oh, that's cool, right? That's just a force problem. Yay! All right, let's keep going. All right, so first we figure that out. And then it says if the tension is 20 newtons, what's the block's speed after a meter? Oh, golly, that's kinematics. If the string tension is 20 newtons and the table is covered with oil, what's the block speed after moving a meter? So what's the difference between B and C? Well, B is it's steel on steel, right? C is steel on steel lubricated. So only difference between this one and this one, just the coefficients of friction. All right, this doesn't sound so bad. Okay, A, let's do A. So this is just force diagram. So there's no reason to, we can just use Randy Knight coordinate system. There's no reason not to. Okay, so force diagram. When in doubt, draw a force diagram. So let's see. It's at rest, right? We want the minimum string tension needed to pull the block. So therefore, what's the friction going to be? Fs max, right? Fs max. Okay, so what are the forces acting on it? It's on a table, and there's always weight. There's only one object, so I can't forget I don't have to worry about subscripts. There's weight, there's the normal, right? There's the tension, and there's Fs max. Okay, that's it. Awesome. And there's friction, so that means you need a normal force, so you do your Y problem first. Okay. So the sum of the Y, okay, hold on, sorry. Is the thing accelerating this way? Of course not. So the sum of the Y forces is 0, right? And what do we have? We have N minus mg. Therefore, N equals mg. So that's what's nice about when you have something on a level ground, on a level surface. The normal is usually equal to mg unless there's some weird thing going on, right? We don't have to worry about angles or anything like that. Okay, so now we have our normal, so that's cool. Now we can do our x. Now obviously the thing is accelerating this way, right? It's at rest and we want to move it. That means it's accelerating. So the sum of the x forces is ma, right? Okay, so what do we have? Using Randy Knight coordinate system, we have T minus Fs max. Okay, but, okay, so what does that say? Oh, but wait a minute. What? Oh, okay, sorry. I said something wrong. All right, so what we want to do is we want to solve for the minimum string tension, right? And so we're going to actually set this equal to 0, okay? We're going to set it equal to 0 with Fs max. And then, in order to get it moving, the tension has to be greater than the tension we're going to solve for. Yeah. Okay, so some of the x forces is 0, so it's T minus Fs max. Okay? Agree? So, therefore, the tension equals Fs max. But what's Fs max? Fs max is mu s n, and we already saw for n, so it's mu s mg. All right? So there you go. All right, so plug in the numbers. So the tension is mu s mg. So mu s, steel on steel, 0.8. And you got to get the right one, right? It's static, you know. So steel on steel dry, static, 0.8. M, 2 kilograms, 9.8. And that comes out to be 15.68 newtons. Okay, now this is the important thing. Look, at this tension, it's not going to move, right? Because we set the forces equal to 0. So at this tension, it's in equilibrium, right? But if the tension is greater than 15.68, it's going to move, okay? That's the important thing. That's why I put this equal to 0, all right? So what we want, in other words, in order for this thing to move, so for the block to move means tension has to be greater than 15.68. I just told you, all right? So the tension has to be greater than 15.68 for the block to move, okay? We found the equilibrium condition where it doesn't move, but if it's just a little bit more than that, it's going to move. Okay, awesome. Okay, so now B, if the string tension is 20 newtons. Now, why did they tell us that? Because 20 newtons is greater than 15.68. So that means it's going to accelerate, all right? That's the important thing. So basically, we're done with part A. We needed to know, if this were 21, if this were 21 newtons, then the B and the C would be 0, right? Because it wouldn't move, you know? But the point is that 20 is greater than 15.68, so it's going to move. Okay, so we're done with A. All right, B, kinematics problem, right? Speed. Okay, how many points do we need? It's at rest, and we want to know the speed after 1 meter, so 2 points. Rainy night coordinate system. You don't even need it. So 0.1, 0.2. So here we go. X, 0, so this is awesome, you know, because it really allows you to get practice for the chapter 2 kind of thing. And we want A to be that way. All right. So here we go. Where do you want to origin? It sort of makes sense right here. But again, it doesn't really matter, you know, it just doesn't matter. Okay, so x0 equals v0 equals t0 equals 0. Love it. x1 equals 1 meter. V1 is what we want. And T1, we don't know. All right. And we don't know A, right? We don't know A. Okay. Well, you know what's coming. So look at all 3 of the kinematic equations. We don't have enough information, right? We can't use any of the 3 kinematic equations with just this information. You know, I mean, we just can't. Sorry. I mean, look at the last one. Like, you know, because we're trying to get V1, right? We're trying to get V final. Well, the last kinematic equation, V final squared equals V initial squared plus 2A delta x. It requires A. We don't know A, you know? So we got to do a force diagram to get A, and no kidding. All right, so we got to get A. in order to solve for V1, okay? Okay, no problem. Let's just do it then. So, force diagram. So what are the forces acting on the block? So there's the string pulling it, so there's tension. It's moving now, right? So yeah, that's okay. It's agree? It's moving. So it's not an Fs max like it was in the previous one. It's a Fk. Then as always, there's an mg at the weight and the normal. All right, there's a friction, so we got to do the y first. Is it accelerating in this direction? No. So the sum of the y forces equals 0, which is n minus mg. Therefore, n equals mg. No kidding, we sort of knew that was coming. Now do the x. It is accelerating in the x direction, so we say ma. So we have a t minus fk. All right, well, that's okay. Fk is mu kn, and n is mg. So, you know, I'm showing you all of the steps, but pretty soon you're not going to do all that. As soon as you see Fk, you're just going to write mu k mg. You know, I mean, right? I hope you do anyway. You don't have to show every little step, you know, but it's okay. All right, so now we have this. All right. So we're trying to solve for A. So we have, in other words, we have ma equals t minus mu k mg. Okay, so you solve for A. So you divide both sides by m, all right? And you just plug it in. I'm not going to do that. I promise you I just plug in all the numbers. And when you do that, I got, well, maybe I should, no, I'll do it. Yeah, I'll do it, why not? So T is 20 newtons. Mu K, dry, steel on steel dry, mu K 0.6. M is 2 kilograms. And good old friend, our good old friend G. Divide that whole mess by M. And the answer is 4.12. 4.12 meters per second squared. All right, so now we're going to do our kinematics. Again, I already said this, but V final squared equals V initial squared plus 2a delta x. Therefore, V1 squared equals V0 squared plus 2a delta x. V0 is 0. Goodbye. Take the square root. So we have square root 2. A is, we just figured out. And delta x is 1 meter. And that comes out to be 2.87 seconds. Yeah. Meters per second. 2.87 meters per second. Yeah. Okay. Part C. I'm not going to do it. But it's okay. Part C, the only thing that's different is instead of putting 0.6, you know, 0.6 was the coefficient of kinetic friction, right? Steel on steel dry. C, it says table's covered with oil. So instead of using 0.6, you're going to use 0.05. So you're just going to put a 0.05 here. And when you do that, the answer comes out to be 4.36 meters per second. Kind of makes sense, right? I mean, if it's covered with oil, you expect it's going to go faster than this. And that's a good check. What if you did your math? So this is when it's dry, right? Steel on steel dry. And this is steel on steel lubricated. What would you do if this was less than that? It's crazy, right? You know you're wrong. So you always want to kind of, you know, don't just be a robot. Look at your numbers and see if they make sense. This has to be bigger than that. Okay, let's quit.